On an observatory screen, a point of light sits beside a spiral galaxy so distant that the galaxy itself is only a soft red smear against the background noise. It was not there in the earlier image. The stars around it have not moved, the detector pattern has not changed, and the same patch of sky has been checked again. The new point is a supernova, a star that has destroyed itself in a galaxy far beyond the Milky Way, and for a few weeks it will shine brightly enough to become a measuring tool for the entire universe. The image does not look dramatic at first. It is a small bright mark among thousands of other marks, recorded by a CCD sensor after photons have crossed intergalactic space for billions of years. Some of those photons were already traveling when Earth had no humans, no cities, no telescopes, and no language for the idea of cosmic expansion. They arrive as numbers, as counts in a detector, as a light curve that rises and fades according to the physics of a dying star. A researcher does not have to imagine the explosion. The evidence is already there in the data. The spectrum carries redshift. The brightness carries distance. The changing light curve carries the signature of a Type 1a supernova, the kind of explosion that can be standardized well enough to act like a cosmic mile marker. And when astronomers began placing these mile markers across deep space, the universe did something they were not expecting. It appeared to be expanding faster than gravity alone should have allowed. That is where dark energy enters the story, not as a visible substance, not as a beam of radiation, and not as a force in the ordinary sense of a push from one object to another. It enters as a discrepancy between expectation and measurement. Galaxies were farther away than a decelerating universe predicted. Supernovae were dimmer than they should have been. The expansion of space itself, instead of slowing down under the pull of all the matter inside it, had begun to accelerate. If these quiet measurements are what keep drawing you back toward the universe, subscribing keeps the next long journey close. The name dark energy can make the idea sound more complete than it really is. It sounds like a discovered substance, as if astronomers found a hidden reservoir spread through the cosmos and labeled it. But the name is more cautious than that. Dark energy is the term given to whatever is responsible for the observed acceleration of cosmic expansion. It describes a measured behavior before it describes a known physical thing. To understand why that matters, begin with something simpler. Galaxies are not flying through space like shrapnel through an empty room. On the largest scales, space itself is stretching. A distant galaxy can remain almost motionless in its own local region and still become more distant from us because the fabric of cosmic distance between here and there is increasing. This is difficult to picture because nothing in ordinary human experience behaves this way. Roads do not stretch while cities sit still on them. Rooms do not grow larger while the furniture remains locally at rest. Cosmologists describe this stretching with a scale factor, a mathematical way of tracking how the distances between very far separated galaxies change with time. If the scale factor doubles, then two galaxies that are not gravitationally bound to each other become twice as far apart in the large-scale sense. The light traveling between them stretches as well, and that stretching is what astronomers record as redshift. A spectral line that should appear at one wavelength arrives shifted toward the red, telling us how much the universe expanded while the light was on its way. This is not a guess made from a single photograph. It is built from spectra, galaxy surveys, the cosmic microwave background, gravitational lensing, supernova light curves, and the statistical pattern of matter across hundreds of millions and billions of light years. The universe is not close enough for direct handling, so cosmology works by comparison. It compares what different kinds of light reveal about distance, age, composition, and motion. Where those independent measurements agree, the picture gains strength. Where they do not, the uncertainty becomes part of the story. The earliest clue that space was expanding came from galaxies. In the early 20th century, astronomers began measuring the spectra of faint spiral nebulae, which later became understood as galaxies outside the Milky Way. Many of those spectra were shifted toward longer wavelengths. The farther the galaxy appeared to be, the greater the shift tended to be. This pattern became known as Hubble's law, though the full history involved several observers, several telescopes, and years of improving distance measurements. A spectrum is a humble object compared with a processed image of a galaxy. It is only light spread into its wavelengths, crossed by lines where atoms and ions have absorbed or emitted radiation. Yet those lines are among the most useful things in astronomy. Hydrogen, calcium, oxygen, and other elements leave patterns that can be identified even when the entire galaxy is a blur. Shift the pattern, and the galaxy's recession becomes measurable. Repeat this for enough galaxies, and the large-scale expansion of the universe begins to appear. At first, expansion did not require dark energy. After the Big Bang, space could be expanding simply because the early universe was already in motion. Gravity would act as a brake. Matter attracts matter, and on the largest scales all the galaxies, gas, dark matter, and radiation in the cosmos should pull back against the expansion. The question was not whether the universe was expanding. The question was how much it was slowing down, and what that slowdown would mean for the ultimate fate of everything. For much of the 20th century, cosmologists considered several possibilities. If there was enough matter, gravity might eventually stop the expansion and reverse it, drawing the universe toward a final collapse. If there was too little matter, expansion would continue forever, but more and more slowly. If the balance was exact, the universe would expand forever while approaching a kind of cosmic halt. These possibilities were not philosophical moods. They were mathematical outcomes tied to density, geometry, and the equations of general relativity. The problem was measurement. To know how the expansion was changing, astronomers needed to compare distances and redshifts over cosmic time. Redshift tells how much the universe has expanded since the light was emitted, but distance is harder. A galaxy's apparent faintness can mean that it is far away, or that it is intrinsically dim, or that dust has absorbed some of its light, or that the object being measured is not the kind of object the astronomer thinks it is. Cosmology depends on knowing the difference. This is why Type 1a supernovae became so important. They are not all identical, but their light curves can be corrected in a way that makes them reliable distance indicators. A Type 1a supernova occurs when a white dwarf in a binary system undergoes a thermonuclear explosion, though the exact pathways can differ. The explosion reaches a peak brightness that can be standardized by how quickly it brightens and fades. If the true brightness can be estimated, then the apparent brightness reveals distance. Picture a white dwarf in a distant galaxy. It is the compact remnant of a star that once fused hydrogen and helium, then shed its outer layers and left behind a dense core, mostly made of carbon and oxygen. In some binary systems, the white dwarf gains mass or interacts with another white dwarf until conditions become unstable. Fusion runs rapidly through the star. In a short time, the remnant is destroyed. The explosion releases enough light to rival the galaxy that contains it. For cosmology, the important thing is not only the violence of the explosion, it is the repeatability. A supernova that can be standardized becomes a candle held up at a known brightness across the universe. The farther away it is, the dimmer it appears. By the 1990s, two teams were using distant Type 1a supernovae to measure whether cosmic expansion was slowing. They expected a break. The data pointed towards something else. The distant supernovae were fainter than they would be in a universe whose expansion was merely coasting or slowing in the expected way. Fainter meant farther. Farther, at the same redshift, meant that the expansion history had not followed the simple gravitational braking model. The expansion had slowed in the early universe, when matter was more dominant, but later it began to speed up. That shift was subtle in the data, but its implication was enormous. In 1998, the evidence for cosmic acceleration became public through the work of the Supernova Cosmology Project and the High-Z Supernova Search Team. The conclusion was surprising enough that it changed the central problem of cosmology. The universe was not just expanding, its expansion was accelerating. Something in the cosmic energy budget behaved as if it had negative pressure, allowing it to drive space apart on the largest scales. The discovery did not mean that individual galaxies suddenly began fleeing from each other under a new local force. The Milky Way is not being pulled apart by dark energy. The solar system is not expanding. Earth is not swelling with the universe. Gravity, electromagnetism, and the forces inside matter dominate on small and even galactic scales. Dark energy becomes important where matter is thinly spread and distances are enormous, where the universe can be treated as smooth enough for its overall expansion to matter. A galaxy cluster shows the difference clearly. Inside the cluster, hundreds or thousands of galaxies orbit within a shared gravitational field, embedded in hot X-ray emitting gas and dark matter. The galaxies do not simply obey the Hubble expansion relative to one another because the cluster is gravitationally bound. But beyond clusters, beyond filaments, across distances where no single structure holds everything together, the expansion of space dominates. Dark energy belongs to that largest scale behavior. The modern picture of the universe divides its contents into components that behave differently as space expands. Ordinary matter includes atoms, stars, gas, planets, dust, and people. Dark matter does not shine or absorb light in ordinary ways, but its gravity shapes galaxies and clusters. Radiation includes photons and other relativistic particles. Dark energy, whatever it is, behaves differently again. As space expands, matter becomes more diluted. Radiation becomes diluted and redshifted. Dark energy, if it is a cosmological constant, maintains the same energy density per volume of space. This one property changes the future. Imagine a box of matter becoming larger. The same particles occupy more volume, so the density drops. Now imagine a component whose density does not drop as the box expands. The larger the box becomes, the more total dark energy-like content it contains, because every new bit of volume carries the same density. In general relativity, that does not violate ordinary conservation in the simple way it would seem to in a laboratory box, because the expanding universe is not a static container. But it does show why dark energy can become dominant late in cosmic history. In the early universe, matter was packed much more densely than it is now. Galaxies were closer together in the scale factor sense. Gas, dark matter, and radiation had far higher densities. Under those conditions, matter and radiation controlled the expansion. Dark energy, if its density stayed nearly constant, was present, but not dominant. As space expanded, matter thinned out. Eventually, the matter density fell low enough that dark energy became the larger component, and the cosmic break turned into an accelerator. That transition did not happen at the beginning. The universe was already several billion years old. A rough way to say it is that after the Big Bang, gravity slowed the expansion for a long time, and only later did the acceleration become important. The exact timing depends on cosmological parameters, but the shift belongs to the relatively recent history of the universe compared with the age of the cosmos. Stars, galaxies, black holes, clusters, and the cosmic web were already well established before dark energy became the dominant influence on expansion. The cosmic microwave background helps fix this picture. It is the afterglow from a time roughly 380,000 years after the Big Bang, when the universe cooled enough for electrons and nuclei to combine into neutral atoms and for light to travel freely. Today that light arrives from every direction as microwave radiation, cooled by expansion to just a few degrees above absolute zero. Its faint temperature variations are tiny, but they encode the density, geometry, and early conditions of the universe. A map of the cosmic microwave background does not look like a photograph of stars. It looks like a modeled sphere, with colors assigned to differences of only tens or hundreds of microkelvin. But inside those differences are the seeds of later structure. Slightly denser regions pulled in more matter. slightly less dense regions emptied out. Over billions of years, gravity amplified those small variations into galaxy clusters, filaments, walls, and voids. The microwave background alone does not show dark energy as a glowing patch. It shows a universe whose geometry and matter content can be inferred with remarkable precision. When combined with other measurements, it points toward a cosmos that is close to spatially flat and whose total energy budget is dominated today by something that is not ordinary matter, not radiation, and not dark matter. In the Standard Model, that dominant component is dark energy. The numbers are often given in rounded form because they depend slightly on the dataset and model. Ordinary atoms make up about 5% of the cosmic energy budget. Dark matter makes up roughly a quarter. Dark energy accounts for about 2/3 or a little more. These proportions do not mean that 2/3 of the galaxies are made of dark energy. They describe the average cosmic inventory in the equations governing the expansion of the universe. To put that in perspective, everything visible in telescope images, every star in the Milky Way, every gas cloud in Orion, every dust lane crossing a spiral galaxy, every planet, moon, asteroid, comet, and human-made spacecraft belongs mostly to the small atomic fraction. Even the enormous black holes at the centers of galaxies are part of that ordinary or collapsed matter side of the inventory. The largest share of the present cosmic budget is inferred from how the universe expands, not from anything a telescope can photograph directly. This does not make the visible universe unimportant. It is through visible and invisible radiation from ordinary matter that the measurements are made. A supernova produces light. A galaxy spectrum provides redshift. Hot gas in clusters shines in X-rays. Neutral hydrogen emits radio waves. Dust glows in infrared. The ordinary matter is the tracer, the luminous ink that lets astronomers read the outline of darker components and the expansion history in which all of it evolves. Dark matter and dark energy are often mentioned together, but they are not the same problem. Dark matter gathers. It clumps under gravity and helps build galaxies. It bends light around galaxy clusters and explains why spiral galaxies rotate faster than visible matter alone would allow. Dark energy does not clump in the same way in the Standard Model. It is smooth, or nearly smooth, and acts on the expansion of space itself. One helps structure form. The other, after it becomes dominant, makes structure formation harder. A simulation of the cosmic web shows the contrast. Dark matter collapses into knots and filaments, forming a network that stretches across the universe. Galaxies form where gas falls into those dark matter halos, cools, and turns into stars. Voids expand between the filaments. Add dark energy to the simulation, and the late universe changes. The expansion speeds up, distant regions move away faster, and the growth of new large-scale structure slows. The web still exists, but its future development becomes limited. This is why dark energy is not only about distance, it is also about time. It changes the history of how the universe moved from a hot early state to the structured cosmos seen today, and it changes what can happen next. A universe without dark energy might keep slowing, allowing gravity more time to gather matter on large scales. A universe with constant dark energy eventually expands so quickly that faraway galaxies drift beyond reachable horizons, not because they vanish locally, but because their future light can no longer overcome the increasing distance. The mathematical door to dark energy was already present before the supernova discovery. General relativity, published by Albert Einstein in 1915, describes gravity not as an ordinary force, but as the curvature of space-time produced by energy and matter. When Einstein applied the theory to the universe as a whole, he found that the equations naturally allowed a dynamic cosmos. Space could expand or contract. A perfectly static universe was not the natural outcome. At the time, the observed universe was often assumed to be static on the largest scales. To allow such a universe in the equations, Einstein introduced the cosmological constant, represented by the Greek letter lambda. In its original use, lambda balanced gravity to keep the universe from collapsing. Later, when cosmic expansion became established, the need for that static balance disappeared. The cosmological constant seemed unnecessary, perhaps even embarrassing. Then the accelerating universe brought lambda back. In modern cosmology, the cosmological constant is one of the simplest ways to represent dark energy. It has a constant energy density and an equation of state with a parameter W equal to -1. That statement can sound technical, but the meaning is direct enough. The component has negative pressure, and in general relativity pressure gravitates too. Negative pressure can drive accelerated expansion. Pressure in everyday life pushes outward. Gas inside a tire presses against the rubber. Steam inside a boiler presses against the walls. Negative pressure is not something people encounter directly in ordinary mechanical systems, and it should not be pictured as a suction pulling galaxies apart. In cosmology, pressure appears in the equations for the expansion of space. A component with sufficiently negative pressure can cause the scale factor to accelerate. The cosmological constant is attractive to theorists because it is simple. It adds one term to the equations and fits many observations well. Supernova distances, the cosmic microwave background, baryon acoustic oscillations, and galaxy clustering can all be described with a model known as lambda CDM, where lambda represents dark energy and CDM stands for cold dark matter. This model has been extraordinarily successful. It does not explain everything, but it provides a compact framework that matches a wide range of data. Success is not the same as complete understanding. If the cosmological constant is vacuum energy, then quantum field theory suggests that empty space should have energy. But naive calculations of vacuum energy produce values wildly different from the observed dark energy density. The mismatch is not small. It is one of the most famous problems in theoretical physics. The observed value is tiny in particle physics terms, yet large enough on cosmic scales to dominate the future of the universe. This is part of what makes dark energy different from many other astronomical mysteries. Astronomers can measure its effect with increasing precision, but the underlying physical explanation remains unclear. It might be a true cosmological constant. It might be a slowly evolving field, sometimes called quintessence. It might indicate that gravity behaves differently on the largest scales than general relativity predicts. Or it might be that current observations contain subtle systematics that have not yet been fully understood. Each possibility has consequences. A true cosmological constant stays the same forever. A dynamic field can change over time, making dark energy stronger, weaker, or more complicated. Modified gravity would mean that the acceleration is not caused by a new energy component at all, but by the way gravity works across cosmic distances. Observations must distinguish these possibilities through their effects on expansion history and the growth of structure. The word forever in the title of this journey should be handled with care. If dark energy is a cosmological constant, then the expansion continues accelerating indefinitely, and the far future becomes increasingly isolated. If dark energy evolves, the future could be different. Acceleration might weaken. It might even reverse in some models, though such outcomes are not established facts. The honest statement is that current evidence strongly supports accelerated expansion, while the physical nature of the cause remains uncertain. Cosmology often advances this way. A pattern appears first. The pattern is measured, challenged, confirmed, refined, and placed into a model. Only later, sometimes much later, does the deeper physical explanation become clear. Neptune was inferred from gravitational effects before it was seen. Dark matter was inferred from motions and lensing before any particle was identified. Dark energy is inferred from the expansion of the universe and from the way structure grows within that expansion. Return to the supernova image, because it shows how the problem became real. A single distant explosion is not enough. One supernova can be affected by dust, calibration errors, gravitational lensing, or unusual intrinsic behavior. Cosmology needs populations. It needs nearby supernova to calibrate the relation between light curve shape and luminosity. It needs distant supernovae observed in multiple filters. It needs spectra to confirm the type and redshift. It needs careful corrections for host galaxies and selection effects. A supernova survey is therefore not a simple search for bright sparks. It is a repeated measurement of the same sky fields. A telescope images a field, waits, images it again, and software compares the frames. New points of light are flagged. Astronomers follow up quickly because the explosion changes from night to night. Spectrographs are turned toward the candidates. Light curves are built, corrected, and compared with templates. Some candidates are rejected. Some become part of the cosmological sample. In the raw data, the universe is not elegant. It is noise, cosmic rays, detector artifacts, weather losses, imperfect subtraction between images, galaxies that are brighter in their cores than in their outskirts, and faint objects near the detection limit. The clean diagram in a paper comes after extensive work. It comes after calibration lamps, standard stars, atmospheric corrections, models of telescope response, and statistical treatment of uncertainty. This does not weaken the discovery. It is what makes the discovery trustworthy. The diagram that matters is the Hubble diagram, where redshift is compared with distance. Nearby objects define the local relation. Farther objects reveal how the expansion rate changed over time. In a decelerating universe, the curve bends one way. In an accelerating universe, it bends another. The distant Type 1a supernovae favored acceleration. Later datasets with many more supernovae have strengthened and refined the result, though they have also revealed how much precision depends on controlling small systematic effects. A difference of a few hundredths of a magnitude can matter when the question is the nature of dark energy. That is why astronomers care about the dust in a host galaxy, the stellar population where the white dwarf formed, the calibration of detectors, and the way a survey selects objects. The acceleration of the universe is not accepted because one measurement seemed exciting. It is accepted because multiple lines of evidence point in the same direction, and because the alternatives must explain all of them together. The Nobel Prize in Physics in 2011 recognized the discovery of the accelerating expansion through observations of distant supernovae. Prizes are human markers placed on a process that is always larger than any award. The science continued before and after. New supernova samples were gathered. Other probes became more precise. The question shifted from whether acceleration exists to what exactly is driving it, and whether its strength has remained constant across cosmic time. Type 1a supernovae remain central because they directly trace the distance-redshift relation. They show how bright standardizable candles appear at different epochs of cosmic history. But they are not the only ruler or candle. Cosmology becomes stronger when it can compare a candle with a ruler, a map of early radiation with a map of later galaxies, and a measurement of expansion with a measurement of clustering. Dark energy leaves a broad signature because expansion affects almost everything on large scales. One of the most important rulers is baryon acoustic oscillation. The name sounds technical, but the physical origin is from the early universe, when ordinary matter and radiation formed a hot plasma. Sound waves moved through that plasma, driven by gravity pulling matter inward and radiation pressure pushing outward. When the universe cooled enough for light to travel freely, the waves left a preferred scale in the distribution of matter. That preferred scale is not a ring drawn in space around every galaxy, but statistically it appears as a slightly higher probability of finding galaxies separated by a particular distance. It is a fossil imprint of early universe sound. As the universe expands, the apparent size of that imprint changes. By measuring it at different redshifts, astronomers can trace the expansion history using a standard ruler that is completely different from a supernova candle. A galaxy survey measures this by collecting redshifts for large numbers of galaxies and quasars. Each redshift adds a point to a three-dimensional map. The sky position gives 2 coordinates. The redshift gives distance along the line of sight after cosmological interpretation. One galaxy tells little. Millions of galaxies reveal patterns. The distribution becomes a map of filaments, walls, clusters, and voids, with the bow scale embedded as a statistical feature. Modern surveys are built for patience. Fibers or robotic positioners place spectroscopic channels on many targets at once. A telescope gathers light from galaxies that may appear as faint dots in imaging surveys. Spectrographs spread that light into wavelengths. Software identifies emission and absorption features, assigns redshifts, and builds catalogs. The result is not a single iconic image. It is a data archive large enough to describe the geometry of the universe. DESI, the dark energy spectroscopic instrument, was designed for exactly this kind of work. It uses thousands of robotically positioned fibers at the Mayall telescope in Arizona to collect spectra from galaxies and quasars. Its aim is to make one of the largest three-dimensional maps of the universe, tracking the expansion history and the growth of structure over billions of years. In recent analyses, DESI data have produced hints that dark energy may evolve with time, though the interpretation remains under active debate. Hints are not the same as a settled revision of cosmology. When a result suggests that dark energy might change, researchers ask whether the signal comes from the universe or from assumptions in the analysis. They compare supernova samples, bow measurements, cosmic microwave background constraints, and lensing data. They examine calibration. They test different models. Attention can be a doorway to new physics, or it can be a sign that a systematic error has survived longer than expected. The recent interest in evolving dark energy does not erase the success of Lambda CDM. It shows how precise cosmology has become. The standard model works well enough that small deviations are now meaningful. Researchers can ask whether the equation of state is exactly -1 or slightly different. They can ask whether it changes with redshift. They can compare how fast structures grow with how fast distances expand. These are not vague questions. They are measurements with error bars. A quasar spectrum in a survey can also carry information from the intergalactic medium. The light from a bright quasar passes through clouds of hydrogen on its way to Earth, leaving a forest of absorption lines. These Lyman alpha forest features trace matter at high redshift when the universe was younger. Combined with galaxy bow measurements, they extend the ruler across a wide span of cosmic history. The farther back the ruler reaches, the better the expansion curve can be reconstructed. The map that emerges is not a map in the familiar travel sense. It cannot be used to steer a spacecraft. Many of the galaxies recorded are so far away that their light began traveling long before the solar system reached its present age. The map is a map of time as much as space. Nearby galaxies show the relatively recent universe. Distant quasars show conditions billions of years earlier. Dark energy is inferred by how the scale of the map changes across those epochs. Another way to test dark energy is to watch how matter clumps. Gravity tries to pull matter into structures. Expansion pulls unbound regions apart. Dark energy accelerates that expansion, making it harder for new large structures to grow late in cosmic history. If astronomers can measure not only distances, but also the growth of cosmic structure, they can test whether the same model explains both. Weak gravitational lensing is one of the tools for this. Massive structures bend the path of light from background galaxies. The effect is usually too small to see in any single galaxy image, but across millions of galaxies it leaves a statistical distortion, a slight alignment in shapes. Measuring that distortion reveals the distribution of matter, including dark matter, along the line of sight. It is a way of mapping mass without requiring that the mass shine. Weak lensing is difficult because galaxies have their own shapes before lensing. Telescopes blur images. The atmosphere distorts ground-based observations. Detectors introduce small patterns. To use weak lensing for cosmology, astronomers must understand the point spread function of the telescope, the redshift distribution of the source galaxies, and many subtle biases in shape measurement. The final cosmic shear map is built from statistics, not from a single obvious arc. Strong lensing, by contrast, can be visually striking. A massive galaxy cluster can bend light from a background galaxy into arcs or multiple images. These arcs are direct evidence that mass curves spacetime, and they help measure the mass in clusters. But for dark energy, the broad statistical lensing field is often more powerful. It tells how structure grows over time, and that growth depends on both the amount of matter and the expansion history. The Dark Energy Survey used a wide-field camera in Chile to image hundreds of millions of galaxies, combining supernovae, weak lensing, galaxy clustering, and galaxy clusters as probes of cosmology. Its results have generally remained consistent with a cosmological constant within uncertainties, while contributing to the broader effort to test whether dark energy is truly constant. This is the nature of the field now. No single probe is enough, and every new dataset becomes part of a larger comparison. The Vera C. Rubin Observatory will add another kind of patience. Its legacy survey of space and time is designed to image the southern sky repeatedly, finding supernovae, mapping weak lensing, tracking asteroids, and recording changes across the sky. For dark energy, repeated imaging matters because it increases the number of transient events and improves the statistical power of galaxy shape measurements. It also creates a moving record of the sky that future astronomers will mine in ways not yet fully planned. Euclid, launched by the European Space Agency, is built to study the dark universe through weak lensing and galaxy clustering from space. Above Earth's atmosphere, its images can have stable shapes that are valuable for measuring tiny lensing distortions. It will survey a large fraction of the sky, mapping galaxies across cosmic time. Its mission is not to take one famous picture, though its images may be beautiful. Its mission is to turn the geometry and growth of the universe into measurable quantities. NASA's Roman Space Telescope will approach similar questions with a wide field of view and infrared sensitivity. It is planned to measure baryon acoustic oscillations, weak lensing, supernovae, and other probes that constrain the dark energy equation of state. Roman will not look at all of space at once. It will build carefully selected surveys, using precise imaging and spectroscopy to extend the map of expansion and structure into epochs where current data remain limited. These missions show how dark energy has changed astronomy itself. The question is so large that it cannot be answered by one instrument or one wavelength. It requires optical images, infrared surveys, spectra, microwave maps, and careful statistical work. It requires a comparison between the smooth background expansion and the lumpy growth of cosmic structure. It requires understanding stars that explode, galaxies that cluster, and light that bends as it crosses the universe. Dark energy is sometimes described as the invisible force expanding the universe forever. That phrase captures the broad idea, but the details are more careful. It is invisible because it does not emit light. It is associated with expansion because it appears in the equations governing the scale of the universe. It may expand the universe forever if it remains constant or behaves in a similar way. But it is not a wind blowing through the Milky Way, and it is not a local pressure prying planets away from the sun. Inside the solar system, dark energy is negligible. The sun's gravity controls planetary orbits. Earth's gravity controls the moon. Electromagnetic forces control the structure of atoms and solid objects. Even within the Milky Way and the local group, gravity binds systems strongly enough that cosmic expansion does not carry them apart. The Andromeda Galaxy is not receding from the Milky Way with the Hubble flow. It is moving toward us, and the two galaxies are expected to merge in the far future. This local exception matters because it prevents a common misunderstanding. Cosmic expansion is not a universal stretching of every ruler, orbit, and body. Bound systems decouple from the expansion. A galaxy is a gravitational system. A star cluster is a gravitational system. A planet is held together by gravity and material forces. The expansion appears between unbound systems on sufficiently large scales, where the average universe can be treated as homogeneous and isotropic. At the scale of galaxy clusters, the boundary becomes more interesting. Clusters can remain bound, but superclusters are often not single-bound objects. Some regions that look connected in maps may not stay together over cosmic time. Dark energy affects which large structures can form, and which apparent associations are only temporary alignments within the expanding web. The universe seen in a deep survey is not a static architecture. It is a structure evolving under gravity while the background space accelerates. The local group, containing the Milky Way, Andromeda, Triangulum, and many dwarf galaxies, will remain a small island of matter compared with the expanding universe around it. Over immense timescales, if dark energy stays constant, galaxies beyond our gravitationally bound neighborhood will become harder to observe. Their light will be increasingly redshifted and diluted. Future observers, if any exist in a merged local group galaxy, may see a sky with far fewer clues that a vast cosmic web ever surrounded them. This does not happen tomorrow. It does not happen on human timescales, or even on the timescales of civilizations as we normally imagine them. The cosmic future is measured in billions, trillions, and far greater numbers of years. Stars will continue to form for a long time, though eventually the gas supply will decline. Existing low-mass stars will burn for trillions of years. White dwarfs, neutron stars, and black holes will remain long after the bright era of star formation fades. Dark energy changes the setting for that future. In a constantly accelerating universe, distant galaxies cross an event horizon in a cosmological sense. Light they emit after a certain time will never reach us, no matter how long we wait, because the intervening space expands too quickly. This horizon is not a wall or a surface a spacecraft could strike. It is a limit imposed by the expansion history of spacetime. The phrase expanding forever, therefore, contains both a simple and a complicated truth. The simple truth is that in the standard cosmological constant model, the universe does not recollapse. Expansion continues and accelerates. The complicated truth is that the future depends on what dark energy actually is. If it changes, the expansion history could change. If it is constant, the isolation of cosmic regions becomes increasingly severe. The data points strongly toward acceleration, but the final physical explanation remains open. Dark energy should also not be confused with inflation, though both involve accelerated expansion. Inflation refers to a very early period, if the theory is correct, when the universe expanded extremely rapidly in a tiny fraction of a second after the Big Bang. It is invoked to explain why the universe is so smooth on large scales, why it appears close to flat, and how tiny quantum fluctuations may have been stretched into the seeds of cosmic structure. Present-day dark energy is far weaker and operates in a very different era. It does not tear the early universe open with explosive speed. It becomes important only after matter has diluted over billions of years. The two phenomena might be related in some deep theoretical way, but that is not established. In narration and in science, it is better to keep them distinct unless a specific model connects them. The early universe was dense enough that radiation and matter shaped nearly everything. Protons and neutrons formed nuclei. Later, atoms formed, and the cosmic microwave background was released. Dark matter guided gravitational collapse. Gas fell into halos, cooled, and formed the first stars. Those stars made heavier elements. Galaxies merged, grew black holes, built disks, lost gas, gained gas, and changed over billions of years before dark energy became the dominant term in the expansion equation. This long delay is one reason dark energy was hard to discover. The acceleration is a late-time effect, visible only when observations reach far enough to compare different eras of expansion. Humans happen to live at a time when dark energy is already dominant, but not so dominant that the evidence of the earlier universe has disappeared. We can still see distant galaxies, the cosmic microwave background, the fossil bow scale, and the growth of structure across a wide range of redshifts. Cosmologists sometimes note this as a coincidence problem. Why is dark energy becoming dominant around the same broad epoch in which observers like us exist? Matter density falls as the universe expands, while a cosmological constant remains fixed. There is a long past when matter dominated, and a long future when dark energy dominates. The transition occurs in a comparatively narrow middle period. Whether that timing has a deep explanation or is simply an observational fact remains unknown. The coincidence problem does not refute dark energy. It is a question about why the measured value has the value it does. Many constants and parameters in physics invite that kind of question. Some may have explanations in deeper theory, some may be environmental, some may remain unexplained for a long time. In cosmology, the problem is sharpened by the fact that dark energy is both tiny in particle physics terms and decisive in the future of the universe. If dark energy is vacuum energy, then empty space is not truly empty. Quantum fields remain present even where there are no particles in the ordinary sense. The vacuum has structure, it can have fluctuations, it can have energy. This idea is not invented for cosmology alone. Quantum field theory treats fields as fundamental. The difficulty is connecting the enormous theoretical estimates of vacuum energy with the tiny value inferred from cosmic acceleration. Some researchers have looked for mechanisms that cancel most of the vacuum energy while leaving a small residue. Others explore dynamic fields whose energy changes slowly over time. A scalar field, spread through space, could roll gradually along a potential, producing negative pressure and accelerated expansion without being exactly constant. These models are often grouped under names like quintessence, though there are many variants. The challenge is to make them fit observations without adding unnecessary complexity. A dynamic field would leave signs. The equation of state parameter might differ from -1. It might change with redshift. Structure growth might not match the simplest cosmological constant prediction. Distances measured by supernovae and bow might curve slightly differently. Future surveys try to measure these differences, but the target is small. Dark energy, if it is changing, is not likely to announce itself with a single obvious event. It would appear as a pattern across many careful measurements. Modified gravity takes another route. Perhaps there is no dark energy component at all. Perhaps general relativity, though extremely successful in the solar system, around binary pulsars, and in gravitational wave observations, needs modification on cosmic scales. In such models, the acceleration comes from the behavior of gravity itself over enormous distances. But modified gravity must pass many tests. It must match local experiments, gravitational waves, lensing, structure growth, and the cosmic microwave background. The detection of gravitational waves from merging black holes and neutron stars has constrained some modified gravity models because gravity waves appear to travel at speeds very close to the speed of light. Any theory that changes cosmic acceleration by altering gravity must survive that and many other constraints. The universe does not allow a new idea to be checked against only the observation it was designed to explain. It must fit everything else too. There are also more exotic possibilities, including interactions between dark matter and dark energy, early dark energy components that briefly mattered in the young universe, and models in which vacuum energy changes through phase transitions. These ideas can be mathematically interesting, but they are not automatically true. The standard model remains the reference because it is simple and successful. Alternatives must earn their place by improving the fit to data in a way that cannot be explained by systematics or statistical fluctuation. This is where the restraint of science becomes important. The phrase mysterious force can invite overstatement. It can make dark energy sound like proof that physics has failed completely. That is not accurate. Physics has described the expansion history with impressive precision. General relativity, Quantum theory, thermodynamics, nuclear physics, and astrophysics all contribute to the modern picture. The mystery lies in the nature of the component or mechanism behind acceleration, not in a total absence of knowledge. A good dark energy model must explain why the acceleration began when it did, why the energy density has the measured value, how the model affects structure formation, and why it has not already been ruled out by other observations. It must handle the universe from the cosmic microwave background to nearby galaxies, from the scale of galaxy clusters to the largest survey volumes. It must make predictions precise enough that instruments can test them. The Hubble constant adds another layer of tension to the story. It describes the current expansion rate of the universe. Measurements based on the early universe, especially the cosmic microwave background interpreted through lambda CDM, give one value. Measurements based on the local distance ladder, using Cepheids and supernovae, tend to give a higher value. The disagreement is called the Hubble tension, and it has persisted despite many checks. The Hubble tension is not identical to the dark energy problem, but the two are connected through the expansion history. Some proposed solutions involve changes in early universe physics, such as early dark energy, that briefly increases the expansion rate before recombination. Others focus on possible systematics in distance measurements. Still others explore modifications to the standard model. None has become the universally accepted solution. A Cepheid variable in a nearby galaxy seems far removed from dark energy, but it can be part of the same ladder. Cepheids have a relation between pulsation period and luminosity. They calibrate distances to galaxies that host Type Ia supernovae. Those supernovae then extend the distance scale far beyond the reach of Cepheids. If any rung of the ladder has a hidden bias, the inferred local expansion rate changes. If the latter is correct, the standard model may be missing something. Other measurements try to avoid the traditional ladder. Water masers orbiting black holes can provide geometric distances in some galaxies. The tip of the red giant branch offers another standard candle. Strongly lensed quasars can act as time delay distance probes when multiple images vary with different arrival times. Each method carries its own uncertainties. The goal is not to find a favored number and defend it. The goal is to understand why the numbers differ. Precision cosmology is now precise enough to reveal these disagreements. Earlier generations worked to establish the broad outlines. The universe expands. Galaxies are external systems. The cosmic microwave background exists. Dark matter is needed, and acceleration occurs. Modern cosmology asks whether a parameter differs by a few percent, whether V is exactly -1, whether neutrino masses leave a measurable imprint, and whether independent datasets agree within their stated errors. That precision can make the universe feel less mysterious in one sense and more mysterious in another. The broad story is clearer than it has ever been. The universe is about 13.8 billion years old. It expanded from a hot, dense early state. It formed light elements, released the microwave background, grew structure, formed galaxies and stars, and entered an era of accelerated expansion. But the details now point toward deeper questions that cannot be answered by broad strokes. A common image for cosmic expansion is dots on the surface of an inflating balloon. As the balloon expands, the dots move away from one another, without any dot being the center of the expansion. The analogy is useful but incomplete. The balloon surface is two-dimensional and embedded in a room, while the universe is not known to be expanding into a larger surrounding space. Still, the analogy helps remove one misconception. The Big Bang was not an explosion from a central point into pre-existing emptiness. A better habit is to think in terms of distances changing everywhere. Any observer in a typical galaxy sees distant galaxies receding, with more distant galaxies receding faster on average. This does not make that observer central. It is what a homogeneous expanding universe looks like from every location. The expansion is not away from us specifically. It is the increase of the scale factor throughout space. Redshift gives this expansion a visible trace. A galaxy with strong hydrogen or calcium lines can have those lines shifted from their rest wavelengths. For nearby galaxies, motion through space can complicate the picture because local gravitational velocities matter. For very distant galaxies, cosmological redshift dominates. The light itself has been stretched during its journey. A photon emitted as visible light can arrive in infrared. A microwave background photon that began as much hotter radiation now arrives cooled by the expansion of the universe. Infrared astronomy becomes essential for the deep universe because of this stretching. The James Webb Space Telescope sees galaxies whose ultraviolet and visible light has been redshifted into infrared wavelengths. Those images are not direct dark energy measurements in the same way as a supernova survey or bow map, but they reveal the early formation of galaxies within the same expanding spacetime. Every deep field is also a record of expansion written into wavelength. When looking at a processed deep field image, it is easy to focus on beauty, arcs, red galaxies, blue knots of star formation, foreground stars with diffraction spikes. But behind the image is a coordinate system, a redshift estimate, a luminosity, and a place in cosmic history. Dark energy is not painted into the image, but it is part of the distance relation that tells how far away those galaxies are and how the space between here and there has grown. The observable universe has a horizon because light has had only finite time to travel since the Big Bang. The most distant light we can see directly is the cosmic microwave background, though we can infer earlier processes through its patterns and through other relics. Dark energy introduces a future horizon as well, if acceleration continues. There will be regions whose current light can reach us now, but whose future light never will. The visible universe becomes a changing window, not an unlimited archive. This is one of the quieter consequences of dark energy. It does not destroy galaxies with spectacle. It separates information. It makes the universe less mutually visible over time. Light from distant galaxies becomes redder, fainter, and eventually inaccessible. The galaxies themselves continue their local histories, forming stars if they have gas, merging if they are bound, orbiting within clusters if gravity holds them. But across the largest distances, communication by light becomes increasingly limited. The far future under a cosmological constant is a long fading, not a sudden ending. The local group merges into a large elliptical-like system over billions of years. Star formation declines as gas is consumed, heated, or locked away. Massive stars disappear first because they burn quickly. Lower mass stars persist for far longer. Red dwarfs may shine for trillions of years. White dwarfs cool. Neutron stars remain dense and dark. Black holes continue to exist on timescales that dwarf stellar lifetimes. Eventually, if known physics continues to apply in the same way, even black holes lose energy through Hawking radiation. Though for stellar and supermassive black holes, the timescales are almost beyond ordinary language. Dark energy does not need to rip them apart in the standard model. It simply sets the background expansion in which isolated bound remnants persist. The future becomes sparse, cold, and increasingly disconnected on cosmic scales. Some dark energy models produce more dramatic outcomes. If the equation of state is less than -1 in a persistent way, sometimes called phantom energy, the acceleration could grow stronger over time. In extreme versions, bound systems would eventually be disrupted in a scenario called the Big Rip. Galaxies, stars, planets, and even atoms could be torn apart as expansion overwhelms all binding forces. But this is not the standard conclusion. It is a model-dependent possibility constrained by observations. Other models allow dark energy to weaken. If acceleration fades, the distant future changes. Expansion might continue without accelerating, or in some models, a recollapse could become possible. These scenarios are not ruled in by current evidence. They remain part of the space of theoretical possibilities, especially as new data test whether dark energy is constant. The fate of the universe is therefore not a finished chapter. It is a calculation waiting for better measurements. The safest statement is that dark energy has already changed the cosmic trajectory. Without it, the future would be governed by matter and curvature in a different way. With it, distant unbound regions recede faster over time. The large-scale universe becomes increasingly dominated by a component whose physical identity is still uncertain. That combination of measurement and ignorance is what makes dark energy one of the central problems in astronomy and physics. There is a human temptation to turn the far future into a moral lesson, but the universe is not arranging its expansion around human meaning. It is following physical laws, some well understood and some not yet understood. The acceleration does not warn. It does not choose. It does not hurry. It appears as a term in equations, a curvature in distance redshift plots, a pattern in galaxy maps, and a question attached to the largest scales we can observe. A night of dark energy observing can begin with ordinary constraints. The weather must cooperate. The telescope mirror must hold its shape. The instrument must be calibrated. The target field must be visible at the right hour. A scheduler balances science priorities, moonlight, seeing, instrument readiness, and survey strategy. The universe may be vast, but the data arrive through hardware, with bolts, cables, cooling systems, motors, software logs, and human decisions. When the shutter opens, photons that have crossed a large fraction of the observable universe strike a detector only a few centimeters across. Some become electrons in silicon. The counts are read out, corrected, and stored. A galaxy that contains hundreds of billions of stars may occupy only a handful of pixels. A supernova can appear as a small excess of light over a host galaxy. A weak lensing distortion can be much smaller than the irregular shape the galaxy already had before its light began the journey. The data then move into archives. Calibration files are applied. Bad pixels are masked. Cosmic ray hits are removed. Astrometric solutions align the image with star catalogs. Photometric calibration turns counts into brightness. Spectroscopic pipelines identify lines and assign redshifts. Quality flags follow the measurements. What reaches a cosmology analysis is no longer just an image, it is a carefully processed set of numbers with uncertainty estimates. This may sound less cinematic than a telescope under a star field, but it is where the universe becomes measurable. Dark energy is not discovered by staring at the sky and feeling that it must exist. It is discovered by reducing uncertainty until a pattern remains. The pattern must survive different instruments, different teams, different statistical methods, and different physical probes. Only then can a claim about the entire universe become more than a story. Even then, the story remains provisional in the scientific sense. Provisional does not mean weak, it means open to revision when better evidence arrives. The acceleration of the universe is well supported. The cosmological constant is a strong and simple explanation, but the exact nature of dark energy remains unsettled, and recent data have made that question more active rather than less. Science can hold those statements together without contradiction. A laboratory experiment can sometimes isolate a phenomenon. Cosmology cannot isolate the universe. There is only one observable universe, and astronomers cannot rerun it with different parameters. They use the sky as a record, with distance serving partly as time. Nearby galaxies show recent conditions. Distant galaxies show earlier ones. The cosmic microwave background shows the universe before galaxies existed. The challenge is to infer a coherent history from all these layers. The difficulty is increased by selection effects. A survey sees what it is able to see. Brighter objects are easier to detect. Dust can hide or redden light. Massive galaxies may be overrepresented compared with faint dwarfs. Supernovae in certain environments may be easier to classify. Quasar spectra depend on target selection. Weak lensing depends on galaxies with usable shapes. Each probe carries a window function, and cosmology must understand the window, before interpreting the view. This is why disagreement between datasets is valuable even when it is frustrating. If supernovae, BAO, CMB, and lensing all point exactly to the same model, confidence grows. If one probe leans away, researchers look for systematics or new physics. If several independent probes lean the same way, the case becomes more interesting. Dark energy research lives in that careful space between skepticism and openness. On the scale of a galaxy, gravity still writes the main story. Spiral arms gather gas and young stars. A central black hole may accrete material and launch jets. Dark matter forms a halo that keeps the rotation curve flatter than visible matter predicts. Supernovae enrich the interstellar medium. Molecular clouds collapse into new stars. Dark energy is present in the equations of the universe, but inside the galaxy, it is not the dominant actor. On the scale of a cluster, gravity binds galaxies, dark matter, and hot plasma into a deep potential well. The intracluster gas glows in X-rays at tens of millions of degrees. Light from background galaxies bends into arcs. Collisions between clusters can separate hot gas from dark matter, revealing the different behavior of visible plasma and invisible mass. Dark energy affects how many clusters form over time and how their abundance changes with redshift, but it does not replace the local gravity holding a cluster together. On the scale of the cosmic web, dark energy becomes harder to ignore. Filaments stretch between clusters. Voids widen. Matter flows along gravitational gradients, but accelerated expansion reduces the ability of distant regions to influence one another. A galaxy in one supercluster and a galaxy in another may share the same cosmic history in the early universe, but their future connection weakens as space expands. The web remains visible now because we live early enough to see it. A void is not truly empty. It can contain dwarf galaxies, thin gas, dark matter, and radiation passing through. But compared with filaments and clusters, it is underdense. Voids expand faster relative to denser regions because there is less gravity resisting the general expansion. Dark energy accentuates this evacuation over time. The large-scale universe becomes more contrasted, with bound islands of matter and increasingly wide regions between them. This contrast began from tiny differences in the early universe. The microwave background shows fluctuations at the level of about 1 part in 100,000. Gravity amplified them. Dark matter fell inward first because it did not interact with radiation the way ordinary matter did. Ordinary matter followed after recombination, forming stars and galaxies within the dark matter scaffolding. Dark energy later slowed the growth of that scaffolding, leaving the cosmic web with a finite future. The fact that small fluctuations became galaxies is one of the reasons cosmology is so interconnected. Change the amount of dark matter, and structure grows differently. Change the amount of ordinary matter, and the acoustic pattern in the microwave background shifts. Change dark energy, and distances and late-time growth change. Every component leaves fingerprints in more than one place. This makes the model testable, but it also means the pieces cannot be understood entirely separately. The discovery of dark energy was surprising partly because it arrived after many astronomers thought the main question was the density of matter. The expectation was that measurements would reveal whether expansion would continue forever or eventually reverse because of gravity. Instead, the measurements showed acceleration. The answer did not simply choose one of the old options. It changed the menu. This kind of change has happened before in astronomy. Earth was moved from the center. The Sun became one star among many. The Milky Way became one galaxy among many. The universe itself became dynamic. Dark matter revealed that visible matter was not enough to explain galactic and cluster motions. Dark energy then showed that even matter, visible and dark combined, was not enough to explain the expansion history. Each step did not make humans less capable of understanding. It made the subject larger than earlier assumptions. The instruments improved. The mathematics became deeper. The evidence widened. The universe did not become magical when it became stranger. It became more physical. Because the strangeness had to be measured, named carefully, and tested against observations. Dark energy continues that tradition. It is unsettling because it is so dominant and so poorly understood. It affects the entire observable universe, yet no detector has isolated it as a particle or field in a laboratory. It shapes the largest possible future, yet it appears in data as a gentle bending of curves and a statistical preference among models. Its scale is enormous. Its observational signature is quiet. A person looking up from a city street will not see dark energy. Light pollution hides many stars, and even under a pristine sky, the visible stars belong mostly to the local Milky Way. The galaxies used to measure dark energy require telescopes. The microwave background requires radio and microwave instruments. Weak lensing requires careful imaging of millions of faint galaxies. The most important part of the universe's current energy budget is not visible to the eye at all. Still, the evidence reaches Earth. It reaches mountain observatories, space telescopes, radio receivers, and data centers. It arrives as photons, not answers. Humans build instruments that turn those photons into measurements. Mathematics turns the measurements into models. The models are tested, debated, revised, and sometimes replaced. This is the only way a short-lived species on one planet can study the fate of a universe it cannot leave. The equation of state parameter W is one of the simplest handles on dark energy. It is the ratio of pressure to energy density, with factors of the speed of light handled in the usual relativistic way. For ordinary non-relativistic matter, pressure is effectively small compared with energy density, so WO is near zero. For radiation is 1/3. For a cosmological constant is -1. Acceleration requires a sufficiently negative pressure. In the equations of cosmology, energy density and pressure both contribute to gravity. A component with positive energy density but strongly negative pressure can cause the expansion to accelerate. This is counterintuitive if gravity is imagined only as attraction between masses, but general relativity treats the universe as a dynamic spacetime whose expansion depends on the stress-energy content as a whole. Measuring double is therefore a major goal. If W is exactly -1 and remains there, the cosmological constant remains favored. If W differs from -1 or changes over time, a dynamic form of dark energy may be needed. The difficulty is that current measurements allow only limited room for deviation. The universe has not handed astronomers a large, easy signal. It has handed them a subtle one. The common parameterization with W0 and WA, often written W0 and WA, tries to describe a value today and an evolution with scale factor. It is not the only possible description, and it may not match the true physics if dark energy is more complicated. But it provides a way to compare datasets. A contour plot in the W0 WA plane can show whether observations prefer the cosmological constant point or lean away from it. Those contours are not final answers. They depend on data choices, priors, calibration, and assumptions about other cosmological parameters. They also show correlations. A change in matter density, curvature, neutrino mass, or the Hubble constant can affect dark energy constraints. This is why cosmological papers often include many plots, many combinations of probes, and careful discussion of systematic uncertainty. For a viewer, the important point is not to memorize every parameter. It is to see the structure of the question. Dark energy is tested by asking how the universe expanded, how structures grew, and whether a simple constant fits both. The data are large and complicated because the universe is large and complicated. The scientific caution is not a weakness, it is the method by which the mystery remains honest. Consider a gravitationally lensed supernova. In a rare system, light from a single exploding star can be bent around a massive foreground galaxy or cluster and arrive as multiple images at different times. The delays depend on the geometry of the lens and the expansion of the universe. Such systems are difficult to find and model, but they offer another route to cosmological distances. The universe provides multiple clocks, but none of them is simple. Consider galaxy clusters counted across redshift. The abundance of massive clusters depends on how structure grows, which depends on dark matter, ordinary matter, initial fluctuations, neutrino masses, and dark energy. Surveys can compare how many clusters exist at different epochs. Too many or too few clusters for a given model can signal a problem. But cluster masses are hard to measure, and the relation between observables and true mass must be calibrated carefully. Consider redshift space distortions. Galaxies do not only follow the smooth Hubble flow, they also fall toward overdense regions under gravity. These motions distort the apparent clustering pattern in redshift surveys. Measuring the distortions gives information about the growth rate of structure. If expansion is accelerating because of dark energy, and if gravity works as general relativity predicts, then the growth rate should match a certain pattern. If it does not, the cause could be new physics or a measurement challenge. Consider the integrated Sachs-Wolf effect, a subtle imprint on the cosmic microwave background caused when photons pass through gravitational potentials that change over time. In a matter-dominated universe, certain potentials remain more constant. In a dark energy-dominated universe, they evolve, leaving a weak correlation between the microwave background and large-scale structure. It is a delicate probe, but it shows again that dark energy is not confined to one observational method. The strongest picture emerges from overlap. A supernova says the distance to a redshift is one thing. Bao says the ruler at that redshift has a certain size. The microwave background fixes the early universe anchor. Lensing measures the mass distribution. Cluster counts measure rare peaks in that distribution. Redshift space distortions measure motion towards structure. When all of these are placed together, dark energy becomes a multi-probe problem rather than a single surprising result. In the first few minutes after the Big Bang, the universe was hot enough for nuclear reactions to build light elements. Hydrogen, helium, and small amounts of lithium emerged from that early furnace. Dark energy did not control that process. Radiation and particle physics did. The predicted abundance of light elements remains one of the pillars of Big Bang cosmology, and it fits with the microwave background and the later formation of stars. Hundreds of thousands of years later, the microwave background was released. Hundreds of millions of years after that, the first stars and galaxies formed. Billions of years after that, galaxies matured, clusters assembled, and heavy elements spread through cosmic gas. Dark energy became dominant only after this long development. It is a late arrival in terms of influence, but once it becomes dominant, it changes the direction of the cosmic future. A star forming in a molecular cloud does not know about dark energy in any meaningful local sense. The cloud collapses because gravity overcomes pressure and turbulence in dense regions. Magnetic fields, radiation, rotation, and feedback shape the process. Planets form in disks around young stars. Comets and asteroids preserve chemistry from early planetary systems. All of this happens inside bound structures. Dark energy provides the background expansion, not the local script. The same is true for black holes. A stellar black hole forms from the collapse of a massive star. A supermassive black hole grows in a galactic center through accretion and mergers. The shadow of a black hole, imaged by radio interferometry, depends on gravity in the strong field regime near the event horizon. Dark energy does not control the size of that shadow, but the number of galaxies, their merger history, and the cosmic time available for black hole growth are all embedded in the expanding universe. This distinction keeps the narration grounded. Dark energy is not an explanation for every unknown in space. It does not replace dark matter. It does not cause supernovae. It does not make stars burn. It does not directly hold galaxies together. It is the name for the component or mechanism causing the accelerated expansion of the universe on the largest scales. Its power is not local drama, but cosmic reach. The next generation of data will not simply ask whether acceleration exists. It will ask whether the acceleration follows the exact pattern expected from a cosmological constant. Euclid will measure shapes and redshifts for vast numbers of galaxies. DESI continues to refine the three-dimensional map built from spectra. Roman will add space-based infrared surveys and supernova measurements. Rubin will repeatedly image the sky, building time domain and lensing datasets of unusual depth. Each instrument has a different personality. A spectroscopic survey values precise redshifts. A weak lensing survey values stable image shapes. A supernova survey values cadence, calibration, and classification. A microwave experiment values temperature and polarization patterns across the sky. Dark energy sits at the intersection. The more independent the methods, the harder it becomes for one shared mistake to imitate a cosmic signal. Future results may strengthen the cosmological constant. They may show that the hints of evolving dark energy fade as systematics are better understood. They may also sharpen those hints into a real departure from lambda CDM. Both outcomes would matter. Confirming a constant with greater precision would deepen the vacuum energy problem. Finding evolution would point toward new fields, new gravity, or some other physics beyond the simplest model. Science does not become less interesting when a simple model survives. A cosmological constant that remains perfectly consistent with better data would still be strange. It would still require explaining why empty space has the measured energy density, why it is so small, and why it now dominates. The absence of change would itself be a fact-demanding explanation. The universe can be mysterious because a model works, not only because it fails. If evolving dark energy is confirmed, the questions multiply. What field is evolving? What sets its potential? Does it interact with dark matter or ordinary matter? Why has it not produced detectable fifth forces in laboratory or solar system tests? Does it remain stable? Does it change the fate of the universe? Each answer would need to connect cosmic expansion with fundamental physics. A curve in a galaxy survey could become a clue to physics far beyond any accelerator. Under the standard model, the future sky of the local group becomes emptier in an observational sense. Galaxies not gravitationally bound to us recede beyond effective visibility. Their light stretches into wavelengths too long and too faint to recover. The cosmic microwave background cools and redshifts until it becomes nearly impossible to distinguish from other backgrounds. Future astronomers in that era might not easily infer the Big Bang from observation, because the evidence available to us now would have faded. This is a striking thought because it means cosmology is time-sensitive. We live at a cosmic epoch when the evidence is rich. The microwave background is still detectable. Distant galaxies still fill deep images. The bow pattern remains measurable. Supernovae occur in galaxies across a wide range of redshifts. The universe has not yet hidden its own history. Dark energy may eventually make that history harder to read. In that sense, the present age is not central, but it is fortunate for observation. Long after the first stars formed, and long before the last stars fade, there is a period when galaxies are numerous. Light still connects distant regions, and instruments can measure the expansion across time. Cosmology is possible because the universe has left enough evidence within our horizon, and because human technology has reached the point of collecting it. The far future also depends on astrophysics inside bound systems. The Milky Way and Andromeda will merge, reshaping their disks into a larger stellar system. Gas clouds may trigger new star formation during the merger, then settle. Stellar encounters will slowly alter orbits. Some stars may be ejected into intergalactic space. Black holes may merge and emit gravitational waves. These events occur within the local island, while dark energy carries other islands away. No spacecraft can outrun the expansion to reach galaxies that become causally disconnected in the far future. Locally, Travel remains limited by energy, technology, and relativity. Cosmologically, the horizon imposes a deeper limit. The universe is not only large, its expansion changes what parts of it can ever exchange signals. Dark energy, therefore, affects not just where matter is, but what can be known from any one location. There is a quiet severity to that limit. Astronomy depends on light arriving. If light cannot arrive, the object becomes inaccessible, no matter how advanced the observer. This is not because the object stops existing, it is because space-time itself sets a boundary on information. The future of an accelerating universe is partly a future of separated histories, each bound region carrying its own stars, remnants, and memories of a once more connected cosmos. That idea can sound lonely, but it is also simply physical. The universe has no obligation to remain observable. The fact that it is observable now, in so many ways, is what makes the present scientific project possible. Every spectrum recorded, every deep image stored, every microwave map refined, is a way of preserving information from an era when the universe still offers a broad view of itself. Dark energy does not make the night sky look different to the unaided eye. It does not announce itself as a new constellation or a moving point of light. Its evidence is cumulative. It is found by comparing the brightness of supernovae, the scale of galaxy clustering, the shape of the microwave background, the distortion of distant galaxy images, and the abundance of clusters. It is a mystery built from precision rather than from spectacle. The reference point for all of this remains the real universe, stars forming from gas, galaxies rotating inside dark halos, clusters bending light, voids widening, and photons crossing expanding space. Dark energy is not separate from that universe. It is part of the same physical description, one term among others, but a term with consequences so large that it changes the ultimate trajectory of cosmic history. Before dark energy, the cosmological constant had already lived several lives. It began as a mathematical adjustment for a static universe. It was set aside after expansion became accepted. It returned as a possible vacuum energy. It became central again after the supernova results. Few ideas in physics have moved so strangely between necessity, embarrassment, convenience, and deep mystery. Einstein's equations allowed lambda from the beginning because the mathematics permitted it. That is important. Dark energy was not added as an arbitrary patch after observations became inconvenient. A term with the right broad behavior already existed within general relativity. The observational surprise was that the universe seemed to require something like it. The theoretical problem is explaining why its value is what we measure. The measured value is extremely small in everyday units. A cubic meter of empty space contains only a tiny amount of dark energy equivalent mass. Locally, this is almost nothing. Across the enormous volume of the observable universe, it becomes dominant. This is one of the strange lessons of scale. A negligible density can govern the fate of everything if it fills enough space and does not dilute as space expands. To see this with an analogy, imagine a faint background that seems irrelevant inside a room. Now extend that background evenly across all intergalactic space, across billions of light years, and allow matter to thin while the background remains. The background eventually wins not by being intense, but by being persistent. Dark energy is powerful because it is everywhere in the model, and because matter becomes less dense as the universe grows. This persistence also explains why the acceleration is gentle by human standards. Galaxies do not jerk away. The expansion rate changes over cosmological time. The effect accumulates across billions of years and enormous distances. A supernova is needed as a marker. A galaxy survey is needed as a map. A microwave background is needed as an anchor. Without such tools, acceleration would be invisible to ordinary experience. Spacecraft that measured the cosmic microwave background, including COBE, MAP, and Planck, did not see dark energy directly. They measured temperature and polarization patterns from the early universe. Those patterns reveal the density of ordinary matter, dark matter, the geometry of space, and the initial spectrum of fluctuations. When interpreted through the Standard Model and combined with late-time data, they help determine how much dark energy is needed today. Planck's map is especially precise. It shows a universe whose early conditions are consistent with a flat lambda CDM model. The peaks in the microwave background power spectrum tell how sound waves moved through the primordial plasma. The angular size of those peaks depends on the geometry and expansion history between then and now. Dark energy affects that distance to the last scattering surface, even though it was not dominant when the microwave background was released. This is one of the subtle strengths of cosmology. A signal from 380,000 years after the Big Bang can constrain a component that becomes important billions of years later, because the light had to cross the entire expanding universe to reach us. The early and late universe are linked by geometry. The cosmic microwave background is not only a baby picture of the cosmos, it is also a backlight shining through the expansion history. When CMB results are combined with BAO, the constraints tighten. BAO gives distances at lower redshifts. The CMB gives the early anchor. Supernovae fill in the distance redshift curve. Lensing and clustering add growth information. The Standard Model survives because it can move through this network of tests without failing catastrophically. The dark energy problem persists because surviving a test is different from revealing the underlying mechanism. If a future measurement finds a convincing departure from a cosmological constant, the microwave background will still matter. Any new model must preserve the early universe successes. It must reproduce the observed acoustic peaks, the abundance of light elements, the formation of structure, and the local tests of gravity. This is why changing cosmology is difficult. The old model is not a loose story, it is a tightly connected structure. Dust is one of the ordinary things that can imitate cosmic effects if it is not handled carefully. Dust in a galaxy absorbs and reddens light from a supernova. Dust between galaxies can also affect light, though usually more weakly. If distant supernovae appear dimmer, astronomers must ask whether the dimness comes from distance or from dust. Multi-wavelength observations help, because dust changes color as well as brightness. Evolution is another concern. A Type 1 supernova in a young star-forming galaxy may not be exactly like one in an old elliptical galaxy. The progenitor systems may differ. Metallicity may differ. Host galaxy environment can correlate with standardized brightness. Modern analyses include corrections for such effects, but the work is delicate. The universe does not provide perfect candles. It provides physical objects that can be made useful only through careful understanding. Selection bias appears whenever a survey preferentially finds brighter objects. At large distances, faint supernovae may fall below the detection limit, leaving a sample skewed toward brighter events. If not corrected, this can distort distance estimates. Survey teams simulate their detection efficiency, model their pipelines, and test how selection affects cosmological parameters. The final result depends on knowing not only what was found, but what could have been missed. Calibration links everything. A tiny error in the response of a detector, a filter transmission curve, or the brightness scale of standard stars can propagate into cosmology. This is why independent instruments matter. It is also why old data are reprocessed when better calibration becomes available. A supernova observed decades ago can still contribute if its photometry is understood, but the confidence depends on how well the entire measurement chain is controlled. Galaxy surveys have their own systematics. Target selection, fiber collisions, redshift failures, stellar contamination, seeing conditions, galactic dust, and survey geometry can all affect clustering measurements. Weak lensing has shape biases and photometric redshift uncertainties. Cluster counts depend on mass calibration. Every probe has vulnerabilities. The power comes from combining probes whose vulnerabilities differ. This is why the dark energy story should not be told as a single eureka moment followed by certainty. The supernova discovery was a turning point, but the decades after it have been a long process of checking, expanding, and refining. The mystery remains not because astronomers failed to measure carefully, but because careful measurement has made the question sharper. Far from the statistical plots, the universe continues its local work. In the Eagle Nebula, pillars of gas erode under radiation from young stars. In the Orion complex, molecular clouds continue turning gas into new suns. In the centers of galaxies, black holes feed when gas reaches them and quiet down when the supply fades. These systems are governed by local physics, but their ages, distances, and histories are embedded in cosmic time. A white dwarf cooling in the Milky Way carries no label saying dark energy. Yet white dwarfs as a population help date stellar systems. Globular clusters help estimate cosmic age. Supernovae from white dwarfs help measure cosmic distances. The same type of object can be a local remnant in one context and a cosmological tool in another. Astronomy often works this way, using ordinary physical systems as rulers, clocks, and tracers. A galaxy cluster like the Bullet Cluster is often discussed in relation to dark matter because its hot gas and gravitational mass are offset after a collision. But clusters also matter for dark energy because their abundance over time depends on expansion and structure growth. The same object can reveal multiple invisible components depending on which measurement is made. X-rays show gas. Lensing shows mass. Redshifts show motion. Counts across time test cosmology. A quasar powered by a supermassive black hole can be seen across enormous distances because accretion converts gravitational energy into radiation efficiently. Its light passes through intervening hydrogen, mapping the cosmic web at high redshift. The black hole itself is a local engine, but the spectrum becomes a cosmological probe. Dark energy is measured partly by using bright objects that formed long before dark energy dominated. A faint dwarf galaxy near the Milky Way can reveal dark matter through its stellar motions. It contributes almost nothing to dark energy measurements directly. Yet the existence of small galaxies, their abundance, and their distribution all depend on the growth of structure. Cosmology connects scales without making them identical. The smallest galaxies and the largest expansion history belong to the same universe, governed by the same overall parameters. The title calls dark energy invisible, and that is true in a strict observational sense. No telescope has taken an image of dark energy. But invisible does not mean unmeasurable. Gravity is invisible in itself, yet its effects are everywhere. Magnetic fields can be invisible until charged particles reveal them. Dark matter is invisible to light, but visible through gravity. Dark energy is invisible through its effect on the scale factor of the universe. The difference is that gravity and magnetism can be tested locally in direct ways. Dark energy is primarily cosmological. Its arena is the entire large-scale universe. A laboratory vacuum chamber does not contain enough volume for the effect to matter. A solar system experiment is dominated by local gravity. The signal becomes significant only when the measurement spans billions of light years and billions of years. This is why dark energy belongs to cosmology rather than to ordinary laboratory intuition. A cosmic mystery can be large without being vague. Dark energy has equations, parameters, data sets, and predictions. It has competing models and statistical tests. It has instruments designed specifically to constrain it. The mystery is not a blank space where anything can be imagined. It is a narrow and demanding problem. What physical component or modification causes the observed late-time acceleration while remaining consistent with everything else we know? This narrowness is important because it protects the subject from becoming fantasy. Dark energy is not evidence for every speculative idea about the universe. It is not a direct sign of alien technology, hidden dimensions in a casual sense, or consciousness shaping space. Some advanced theories may involve extra dimensions or fields, but they must be expressed mathematically and tested observationally. The evidence is cosmic expansion, not permission to invent without constraint. The restraint does not make the subject smaller, it makes it more remarkable. A tiny term in an equation, supported by faint supernovae and galaxy maps, can determine whether the observable universe becomes more isolated forever. A measurement of a spectral line in a distant galaxy can help test the fate of space. The path from photon to future is long, but it is physical at every step. The timeline of dark energy begins long before the name. General relativity allows dynamic spacetime. Galaxy redshifts reveal expansion. The cosmic microwave background confirms a hot early universe. Dark matter becomes necessary to explain structure. Supernovae reveal acceleration. Large surveys refine the expansion history. Each stage adds a layer. None replaces all the earlier layers. The modern picture is cumulative. At 380,000 years, the microwave background is released. At hundreds of millions of years, the first stars ignite. Over the next several billion years, galaxies assemble and enrich themselves with heavier elements. Around the time the solar system forms, the universe is already entering a dark energy-dominated era in the broad cosmological sense. Earth forms inside a galaxy that is locally bound, while the largest-scale expansion begins accelerating around it. This overlap is easy to miss. The solar system is about 4.6 billion years old. The acceleration of the universe became important in roughly the same broad era, though not because Earth matters. The timing is a coincidence from the cosmic point of view. While planetesimals collided in the young solar system and the early Earth cooled, the background expansion of the universe was changing character on scales far beyond the local group. Life on Earth evolved entirely within an accelerating universe. Every fossil, every ocean, every continental drift, every mass extinction, every mammal, every human culture occurred after dark energy had become significant in the cosmic expansion. Yet no organism needed to know this to survive. The acceleration is woven into the largest background, not into the day-to-day physics of a biosphere. Only when intelligence built instruments capable of measuring galaxies did the background become visible. The discovery required glass, mirrors, photographic plates, electronic detectors, rockets, cryogenic instruments, computers, statistics, and a long chain of previous astronomy. Dark energy is ancient in effect, but recent as knowledge. For most of Earth's history, it was shaping the cosmic future without any local witness. A cosmological event horizon is different from a black hole event horizon, though both involve limits on communication. A black hole horizon surrounds a region from which light cannot escape to faraway observers. A cosmological horizon arises because accelerated expansion prevents light emitted beyond certain conditions from ever reaching us. It is not caused by a central mass. It is caused by the global behavior of spacetime. This horizon means that there are galaxies whose light we see today, but whose future light will never arrive. We observe them as they were, not as they are now, and never as they will be in the far future. Astronomy already deals with look-back time, but dark energy makes the separation permanent for increasingly many regions. The universe becomes not only old and large, but causally partitioned. The word forever is therefore not a single visual scene. It is an increasing redshift, a fading background, a thinning supply of reachable galaxies, a local group remaining bound while everything outside it recedes beyond communication. It is the scale factor growing without turning around. It is not an explosion. It is the continuation of expansion under a dominant component whose density does not dilute like matter. If dark energy is constant, the expansion approaches a state called de Sitter expansion, named after Willem de Sitter. In such a future, the universe becomes increasingly empty from the viewpoint of any given observer, with a horizon and a nearly constant expansion rate in a particular sense. Real astrophysical structures remain locally complex for enormous spans of time, but the large-scale background tends toward a simple, cold, accelerating geometry. This future is not certain, because the nature of dark energy is not certain. But it is the future suggested by the simplest model that fits much of the data. Cosmology has to hold the model and the uncertainty together. It can say, if lambda is constant, this is what happens. It can also say, if new measurements show evolution, the fate must be recalculated. That conditional language is not evasive. It is accurate. The first supernovae that revealed acceleration are now long faded. Their host galaxies remain in the sky, but the brief points of light used to measure them are gone. What remains are archived images, spectra, light curves, calibration files, and papers that turned fading stars into evidence for the expansion history of the universe. The explosions were temporary. The implication has lasted. Somewhere tonight, a telescope may be collecting light from another supernova in another galaxy. The photons enter the mirror after crossing space that has stretched during their journey. The detector records the event without knowing its meaning. Meaning comes later. When the light curve is fit, the spectrum measured, the redshift assigned, the distance compared, and the point added to a diagram that reaches across billions of years. Elsewhere, a spectroscopic survey is placing fibers on galaxies. A robotic positioner moves by millimeters so that a glass fiber can catch the light from a galaxy billions of light years away. Thousands of such fibers collect thousands of spectra. The result is a map too large to see at once, a map made from redshifts, each redshift a small statement about expansion. Dark energy is tested by the accumulation of these small statements. Above Earth, a space telescope holds its temperature steady and points at a field of faint galaxies. Their shapes must be measured with extraordinary care, because the lensing signal is tiny. The galaxies are not chosen for beauty, though many are beautiful. They are chosen because their distorted images carry information about the matter between them and us, and about how cosmic structure has grown under the influence of gravity and expansion. In a data archive, a microwave map remains available to anyone with the tools to use it. It is a record of the young universe, but also a boundary condition for the present one. The modeled pattern of tiny temperature differences connects to galaxy maps, supernova distances, and the dark energy term. The early universe and the accelerating universe are separated by billions of years, yet joined by light. This is the actual texture of the mystery. Not a single dark shape moving through space, not a hidden engine at the edge of the cosmos, but a network of evidence that points to acceleration. It is the dimness of supernovae. It is the scale of galaxy clustering. It is the geometry implied by the microwave background. It is the slowed growth of structure. It is the inability of ordinary matter and dark matter alone to account for the expansion history. The universe, in this picture, is not merely growing older, it is changing in the relation between its parts. Regions that were once more connected become less able to exchange light. The cosmic web remains, but its future growth is limited. Galaxies keep their local histories, but the background between unbound systems expands faster. Dark energy is invisible because it has no surface, no color, and no spectrum of its own. It is known by what the whole universe does. A final answer may come from future surveys, or from a theoretical breakthrough, or from an unexpected tension that refuses to disappear. It may reveal that dark energy is a true cosmological constant, a property of space-time itself. It may reveal a field that changes slowly across cosmic history. It may reveal that gravity must be understood differently at the largest scales. Or it may show that the simplest model is still the best description, leaving the deeper why for another generation. For now, the measurements continue. Mirrors collect ancient light. Spectrographs separate it into lines. Detectors count photons from galaxies whose present state is already beyond direct knowledge. Computers compare maps with models. Scientists argue over uncertainties small enough to matter. The universe expands while it is being measured, and the measurements show that the expansion is not slowing in the way gravity alone once suggested. The point of light on the observatory screen fades over weeks until it disappears back into the soft glow of its host galaxy. The file remains. The redshift remains. The distance estimate remains. One supernova cannot explain the universe, but thousands of them, joined with maps of galaxies and ancient microwave light, have changed the question we ask about the future. The sky returns to looking almost the same. Stars over Earth keep their familiar patterns for another night. The Milky Way arches overhead in dark places. And far beyond those visible stars, beyond the galaxies bright enough for small telescopes, beyond clusters and filaments and the widening spaces between them, the scale of the universe continues to grow, carried by something still unnamed in its deepest nature, measured only by the slow acceleration of everything too distant to hold together. The word energy itself requires care. In everyday speech, energy is something stored in fuel, carried by electricity, released in heat, or used to move an object. In cosmology, energy density is part of the stress energy content that tells space-time how to evolve. Dark energy does not behave like a tank of fuel being burned. It is not being consumed by the expansion in the way a rocket consumes propellant. It is a property assigned to the large-scale universe because the expansion behaves as if such a component is present. That distinction prevents a misleading question. Where is the engine? There may be no engine in the mechanical sense. If dark energy is a cosmological constant, it is not located in one region more than another. It is not strongest near galaxies or weakest in voids in the usual model. It is associated with space itself, the same everywhere at the level of the smooth cosmic background. The acceleration comes from the equations of the whole universe, not from a machine hidden in it. The smoothness of dark energy is itself testable. If dark energy clustered strongly, it would affect structure in ways that could be measured. Most observations so far are consistent with a smooth component, though the details depend on the model. A scalar field can have perturbations, but their behavior may be suppressed depending on the field's properties. Modified gravity can mimic smooth dark energy in distances while changing growth. The question is not only how much dark energy exists, but whether it has texture. Texture in cosmology means statistical pattern. A galaxy survey does not ask whether one particular galaxy looks lonely. It asks how galaxies are distributed compared with random expectations. It measures correlations at different separations. It measures power spectra. It measures how clustering changes with redshift. The universe becomes a field of probabilities, and dark energy is constrained by how those probabilities evolve over time. This can feel far removed from the physical universe of stars and gas, but the statistics are built from real objects. Each point in a catalog corresponds to a galaxy, with stars, dust, gas, and a dark matter halo. Many contain black holes. Some are forming stars rapidly. Others are old and quiet. Cosmology temporarily strips away those details to use the galaxies as tracers, but the tracers are still physical systems with their own histories. The same is true for supernovae. A cosmological analysis may treat them as distance indicators, but each one is the end of a stellar remnant. A white dwarf accumulates mass or merges. Carbon ignites under extreme density. A thermonuclear flame or detonation unbinds the star. Nickel decays into cobalt, and then iron, powering the light curve. The cosmological candle is also a stellar death, and that dual identity gives the measurement both power and complexity. Because Type 1a supernovae involve stellar populations, they connect cosmology to galactic archaeology. The age and metallicity of stars in the host galaxy may affect the explosion. Star-forming galaxies and old elliptical galaxies may produce slightly different populations. Astronomers do not ignore this. They include host mass corrections and compare subsamples. The better the supernovae become as tools, the more their astrophysics matters. There is a pattern here that repeats across dark energy research. A probe begins as a simple idea. Supernovae are candles. Bow is a ruler. Lensing maps mass. Clusters count growth. Then, every probe becomes complicated because the universe is physical, not idealized. Candles have environments. Rulers have reconstruction methods. Lensing has shape noise. Clusters have mass calibration. The challenge is to keep the simple cosmological signal while respecting the messy astrophysics that carries it. This is why long surveys matter more than isolated detections. A survey can characterize its own selection. It can compare fields. It can use overlapping data. It can repeat measurements. It can discover enough objects that rare outliers do not control the result. Dark energy is a statistical problem because the signal appears across populations and cosmic volumes. The universe is too large for shortcuts. The cosmic distance ladder is one of the oldest examples of building knowledge in layers. Parallax measures nearby stars by Earth's orbit around the Sun. Cepheids extend distances to nearby galaxies. Type 1a supernovae extend farther. Each rung depends on the previous one. Space missions like Gaia improve parallax measurements, which improve Cepheid calibration, which improve supernova distances, which sharpen the local expansion rate. A spacecraft mapping stars in the Milky Way can therefore influence dark energy debates. Baryon acoustic oscillations use a different foundation. Their scale is set by early universe physics and calibrated through the microwave background. This makes Bow less dependent on the local distance ladder. When Bow and supernovae agree, confidence grows. When they lean differently, the difference becomes informative. Independent foundations are valuable because they reduce the chance that one hidden calibration issue controls the entire cosmological picture. The cosmic microwave background is also not free of assumptions. Interpreting it requires a model for the early universe, the composition of cosmic components, recombination physics, and the statistical nature of primordial fluctuations. The model works extremely well, but its parameters are not measured in isolation from theory. This is another reason late-time probes matter. They test whether the universe evolved from the early conditions in the way the model predicts. If the early universe predicts one present expansion rate and local measurements find another, the tension could mean hidden error, or it could mean missing physics. If dark energy measurements from distances and growth disagree, the same possibilities arise. Cosmology is now full of such cross-checks. The field has moved from discovering the broad model to stress testing it. The stress tests are not signs that cosmology is collapsing. They are signs that it is mature enough to be precise. A map with no details cannot show small inconsistencies. A precise map can. The more carefully astronomers measure the universe, the more they can see where the model is strong and where it may bend. Dark energy sits at one of those bending points. A useful way to think about dark energy is as a question written across three curves. The first curve is the expansion history, measured by distances at different redshifts. The second curve is the growth history, measured by how matter clumps over time. The third curve is the early universe anchor, measured by the microwave background and primordial physics. The correct explanation must pass through all three. If a model changes the expansion but leaves growth wrong, it fails. If it fits growth but ruins the microwave background, it fails. If it explains the Hubble tension but predicts forces not seen in the solar system, it fails. This is why the solution to dark energy has not been simple. The universe is overconstrained in useful ways. It offers many tests and few places for a careless theory to hide. The observational situation in the mid-2020s is therefore active but not chaotic. The standard cosmological constant remains a powerful baseline. DESI and other datasets have raised renewed interest in possible evolution. Supernova analyses continue to improve. Euclid, Roman, Rubin, and other projects will add major new constraints. The field is not waiting for one magic picture. It is building a network of evidence dense enough to distinguish small differences in cosmic history. Those small differences may decide the largest possible question. If V equals -1 exactly, the future is the long accelerating expansion of lambda CDM. If W changes, the future may be different. A small shift in a parameter measured from distant galaxies can change whether the universe approaches de Sitter, like isolation, weakens its acceleration, or follows some more complicated path. The fate of the cosmos is written in decimals. The decimals are difficult to earn. They require stable instruments, careful calibration, long observing campaigns, and teams large enough to handle imaging, spectroscopy, theory, simulations, data management, and statistics. A dark energy paper may have hundreds of authors because the measurement is not the work of one person staring through an eyepiece. It is a technical structure built across institutions and years. This scale of collaboration mirrors the scale of the problem. No single telescope can see the whole story. No single wavelength contains all the evidence. No single equation explains the value of dark energy in a satisfying way. The universe is approached by pieces, and dark energy is inferred from how the pieces fit. When they fit too well, the simplicity is suspicious in a deep theoretical sense. When they do not fit perfectly, the discrepancy becomes a possible clue. A simulation running on a supercomputer offers another kind of evidence. Researchers set initial conditions based on the microwave background, choose cosmological parameters, and let gravity evolve the matter distribution. They compare the simulated web with galaxy surveys. They vary dark energy models and watch how distances and growth change. Simulations do not replace observations, but they show what different universes would look like if their parameters were different. In these simulations, dark matter forms the backbone. Gas physics adds complexity. Star formation and feedback from supernovae and black holes shape galaxies. Dark energy changes the expansion background and suppresses late growth. Because galaxies are messy, cosmologists often use large scales where the details of star formation matter less. Even so, connecting observed galaxies to underlying matter requires models, mock catalogs, and careful uncertainty estimates. Mock catalogs are artificial universes built to test analysis methods. They allow researchers to run a pipeline on data whose true cosmology is already known. If the pipeline recovers the correct answer, confidence grows. If not, biases can be identified before real data are interpreted. Dark energy research, therefore, involves not only observing the universe, but creating controlled imitations of it to test the machinery of inference. The machinery matters because the signal is subtle. Cosmic acceleration is not measured by watching a galaxy speed up in real time. Human lifetimes are too short. Instead, astronomers compare different distances, different epochs, and different statistical patterns. They reconstruct a history from light already in transit. The universe is observed as a layered archive, and dark energy is one of the conclusions drawn from reading that archive correctly. A faint galaxy in a deep image may be billions of light years away, but its redshift is not automatically known from the image alone. Photometric redshifts estimate distance from colors using the way spectral features move through filters. Spectroscopic redshifts are more precise because they identify lines directly. Large surveys often combine both. Weak lensing may use photometric redshifts for enormous numbers of galaxies, while bow measurements prefer spectroscopic precision. The choice depends on the probe. Photometric redshift errors can blur cosmic measurements. If galaxies are assigned to the wrong distance bins, lensing and clustering signals shift. Spectroscopic calibration samples help correct this. Space-based imaging helps by adding stable infrared data. Ground-based surveys add depth and repeated coverage. Dark energy constraints become stronger when different observing strategies support one another. The cosmic web itself is not frozen. Galaxies move within it. Clusters accrete matter. Voids empty out. Filaments channel gas and galaxies toward denser knots. Dark energy slows the growth of this web at late times, but it does not erase what already formed. The structures visible today are fossils of earlier gravitational growth and active systems still evolving within local gravity. A galaxy filament can stretch for hundreds of millions of light years, connecting clusters like threads in a vast network. The galaxies within it are not physically connected by solid material, but by the shared gravitational structure of dark matter and matter density. Between filaments, voids can span enormous volumes with relatively few galaxies. Dark energy does not create the web, but it shapes the rate at which the web can continue to sharpen. In a universe dominated only by matter, structure would keep growing more effectively. In a dark energy-dominated universe, expansion increasingly wins on large scales. Existing bound structures remain, but new large structures have difficulty forming. This is a subtle form of cosmic aging. The universe does not simply run out of time, it changes the balance between gravity's gathering tendency and expansion's separating tendency. That balance is present in the Friedmann equations, which come from applying general relativity to a homogeneous and isotropic universe. These equations relate the expansion rate to matter, radiation, curvature, and dark energy. They are not decorations added after observation, they are the mathematical skeleton of modern cosmology. The supernovae, BAO, CMB, and lensing measurements supply the values that fill the skeleton with a specific cosmic history. Curvature is another part of the story. A universe can be spatially flat, positively curved, or negatively curved in the large-scale geometric sense. Observations indicate that the universe is very close to flat. In a flat universe, the total density equals a critical value. Ordinary matter and dark matter together fall short of that value. Dark energy helps fill the gap. This is one reason the microwave background and acceleration evidence fit together. Flatness does not mean the universe is two-dimensional or visually flat. It means that the geometry of large-scale space follows Euclidean rules to high precision, so parallel lines behave in the familiar way across cosmic scales. The microwave background's acoustic pattern is sensitive to this geometry. The fact that the observed pattern matches near flatness constrains the total energy density, strengthening the case for a dominant dark component beyond matter. Neutrinos add another subtlety. They are real particles with very small masses, and they affect the growth of structure because they move rapidly in the early universe and suppress clustering on certain scales. Cosmological data can constrain the sum of neutrino masses. This matters for dark energy because parameters can be correlated. To measure one component precisely, the others must be handled carefully. The universe does not separate its unknowns for human convenience. Radiation, ordinary matter, dark matter, neutrinos, curvature, dark energy, and the initial fluctuation spectrum all contribute to the final interpretation. A change in one can mimic or compensate for a change in another over some range. Breaking these degeneracies requires multiple probes. This is why cosmology has become a science of combinations: CMB plus BAO, BAO plus supernovae, lensing plus clustering, local distances plus early universe anchors. The combinations are powerful, but they must be interpreted honestly. If two datasets are in tension, simply combining them can produce a precise number that hides the disagreement. Responsible analyses show the separate constraints as well as the combined result. They ask whether the datasets are statistically consistent. They test robustness. Dark energy is too important a question to be answered by averaging away discomfort. The next decade may therefore be decisive, not because it will end mystery, but because it will reduce the space of viable explanations. If Euclid, Roman, Rubin, Deci, and other surveys all agree with a cosmological constant at high precision, dynamic dark energy models will face tighter constraints. If they find consistent deviations, the standard model will need revision. Either way, the universe will have spoken through a larger and cleaner set of measurements. Even a revision would likely preserve much of the current framework. The Big Bang model, the microwave background, nucleosynthesis, dark matter, and the expanding universe would not vanish because W changed slightly. Science usually refines rather than erases. A better dark energy theory would have to contain the successful older model as an approximation, explaining why lambda CDM worked so well for so long. That is how general relativity replaced Newtonian gravity without making Newton useless. Newton's laws still work for many everyday and solar system calculations. General relativity becomes necessary in strong gravity, high precision, and cosmology. A future theory of dark energy or gravity may similarly preserve general relativity where it has been tested while extending it where cosmic acceleration demands more. The humility required by dark energy is not the humility of surrender, it is the humility of scale. The phenomenon is measured across billions of light years. The cause may involve vacuum physics, fields, or gravity in regimes far beyond ordinary intuition. Human instruments are small, temporary, and local, yet they are precise enough to detect a change in the expansion history of the universe. That combination is difficult to overstate without exaggerating it. A mountain telescope under a dark sky is not outside the universe it measures. It is made of atoms from earlier generations of stars. Its mirror was polished on a planet orbiting one ordinary star in one galaxy. Its detectors are cooled by human engineering. When it records a galaxy spectrum, matter inside the universe is measuring the expansion of the universe. Dark energy is therefore not only an external subject, it is part of the environment that made the measurement possible. The same atoms in the telescope and in the observer belong to the 5% ordinary component. The gravity holding the galaxy together depends heavily on dark matter. The large-scale expansion is dominated by dark energy. Every observation is made from inside this layered cosmic inventory. The observer is not separate from the budget being measured. The observer is a small arrangement of one component, inferring the behavior of the rest. This does not make the inference subjective. The spectra are real. The redshifts are measurable. The supernova light curves can be shared and reanalyzed. The microwave maps can be compared. The galaxy catalogs can be tested. Science works because observations can outlast the individual observer. Dark energy remains mysterious, but the evidence for acceleration is not a private impression. It is a public record of measurements. A final theory, if it comes, may make the name dark energy feel outdated. Perhaps it will be folded into a deeper understanding of space-time. Perhaps lambda will be derived from a principle not yet known. Perhaps a field will be identified through cosmology alone. Names often come before understanding. The important thing is that the name keeps attention on the measured effect without pretending the physical story is complete. Until then, the universe continues to provide signals. A galaxy cluster bends background light. A supernova brightens and fades. A quasar spectrum is crossed by absorption lines. A microwave photon arrives after traveling since the universe became transparent. A red galaxy in an infrared frame shows that its light has been stretched by expansion. None of these signals alone is dark energy. Together, they trace the universe in which dark energy dominates. The invisible force expanding the universe forever is therefore a title with a careful center. Invisible, because no light comes from it. Force, only if the word is used broadly for the effect on expansion rather than a local push. Expanding, because the scale factor accelerates. Forever, if the simplest model remains correct. Every word points toward a real measurement and also toward a caveat. That is where the subject lives. At the edge of a deep field, a tiny red galaxy may be almost lost in noise. Its light has crossed so much expanding space that its original colors have shifted beyond what human eyes can see. A telescope gathers it anyway, a catalog stores it, a redshift estimate places it in time. The galaxy becomes one point in a much larger attempt to understand how space itself has changed. The universe has not given a final explanation for dark energy. It has given distance indicators, rulers, backgrounds, distortions, and maps. It has given enough evidence to show acceleration and enough uncertainty to keep the deepest question open. That balance is not a failure of knowledge. It is the present frontier. The mystery is no longer whether the universe is expanding. It is why the expansion is accelerating, and what that means for everything that is not gravitationally held together. The observatory screen will keep filling with small marks. Some are nearby stars. Some are galaxies. Some are detector artifacts that must be removed. Some are supernovae, briefly visible across immense distances. The work is slow because the question is large. The answer, when it comes, may not look dramatic at first. It may appear as a small shift in a contour plot, a cleaner agreement between probes, or a deviation that refuses to disappear. Dark energy asks for that kind of patience. It is not a mystery solved by one night of looking up. It is a mystery measured by decades of watching the universe from many angles, with instruments that turn faint light into numbers and numbers into history. The future of cosmic expansion is hidden in those numbers, and the numbers keep arriving, one photon at a time. A Hubble diagram can look almost modest compared with the conclusion drawn from it. It is a set of points with error bars, a curve passing among them, and labels that refer to redshift and distance modulus. Yet inside that graph is a history of the scale factor. Nearby supernovae anchor the low redshift end. Farther ones show the universe when it was younger. The bend of the curve is not decorative. It is the trace of cosmic acceleration encoded in brightness. Distance modulus is another example of astronomy turning the unreachable into arithmetic. It compares how bright an object appears with how bright it truly is. A difference of 5 magnitudes corresponds to a factor of 10 in distance. The system comes from the old magnitude scale of naked eye astronomy, yet it now helps measure galaxies billions of light years away. Old observational language survives inside modern cosmology because the sky has always required indirect measurement. The units themselves can become difficult. A light year is the distance light travels in 1 year, about 9.46 trillion kilometers. A megaparsec is about 3.26 million light years. Cosmologists often use megaparsecs because galaxies and clusters live on such scales. The Hubble constant is commonly expressed in kilometers per second per megaparsec, a unit that sounds awkward until you realize it is describing how recession speed increases with distance in an expanding universe. At small distances, peculiar velocities interfere with the Hubble flow. A galaxy may move toward a cluster or orbit within a group at hundreds of kilometers per second. That motion can be larger than the smooth expansion over short distances. To measure dark energy, astronomers go farther out, where the expansion signal dominates over local motions. The universe has to be sampled on scales large enough that individual gravitational habits average into a cosmic pattern. This averaging is not a denial of complexity. It is a recognition of scale. The universe is lumpy on the scale of stars, galaxies, and clusters. On sufficiently large scales, the lumps average out, and the cosmos becomes statistically homogeneous. Cosmology depends on that transition. Dark energy is not measured from the motion of one galaxy, but from the behavior of the large-scale universe after local complexity has been accounted for. The cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales, is supported by observations, but remains an assumption tested continually. Galaxy surveys check whether matter distribution smooths out at large enough scales. The microwave background shows remarkable uniformity after removing the effects of our motion and foreground emission. If the universe were radically different in different directions on the largest scales, dark energy measurements would have to be rethought. Some alternatives to dark energy have tried to explain acceleration by placing us near the center of a huge cosmic underdensity, where the apparent expansion might differ from the global average. Such models generally struggle with the microwave background, galaxy surveys, and the lack of evidence that we occupy a special central position. The simpler explanation remains a broadly uniform component or modification affecting the whole large-scale universe. Foregrounds are another part of the work. The Milky Way contains dust that absorbs and emits light. It contains synchrotron radiation from charged particles spiraling in magnetic fields. It contains free emission from ionized gas. Microwave background measurements must remove these foregrounds. Optical surveys must account for galactic dust. Even when studying the largest scales, astronomers must first understand the material in their own galaxy. This is a useful reminder of where every observation begins. A photon from a distant galaxy passes through intergalactic space, enters the halo of the Milky Way, crosses the dust and gas of our galaxy depending on direction, passes through Earth's atmosphere if the telescope is on the ground, reflects from mirrors, enters an instrument, and becomes an electronic signal. Each stage can alter or limit the measurement. Cosmology is cosmic, but the measurement chain is local. Space telescopes remove the atmosphere, but add their own constraints. They need stable pointing, thermal control, radiation protection, communication links, and carefully planned observing programs. A space telescope cannot be repaired easily, and its instruments must be understood over years as detectors age and conditions change. The absence of air is an advantage, but not a guarantee of simplicity. Ground observatories have different strengths. They can be larger, repaired, upgraded, and connected to massive instruments. They can host spectrographs with thousands of fibers and cameras with huge focal planes. They deal with weather and atmosphere, but they also collect enormous datasets night after night. Dark energy research uses both ground and space because the strengths are complementary. The scale of future surveys means that human eyes will not inspect most of the data directly. Algorithms will detect supernova candidates, estimate galaxy shapes, assign photometric redshifts, flag artifacts, and build catalogs. Human judgment remains essential, but it operates through code, validation, simulations, and statistical review. The modern observatory includes the data center as much as the dome. Machine learning may help classify objects and identify patterns, but it does not remove the need for physical understanding. A model can find correlations that are useful without explaining them. For dark energy, correlations must be connected back to selection effects, calibration, astrophysics, and cosmology. Otherwise, an algorithm may become another source of hidden bias. The universe is too important a dataset to treat as a black box. The deepest challenge is that dark energy is inferred from an integral history. Light from a supernova carries the result of expansion over the whole path it traveled. The distance to the microwave background depends on the expansion across nearly the entire history of the universe. Bow distances depend on both the standard ruler and the expansions since the relevant epoch. Untangling when dark energy mattered requires comparing many redshifts and many probes. This is why the word redshift appears so often. Redshift is the time coordinate of observational cosmology, though it is not time itself. Higher redshift generally means earlier cosmic time and greater stretching of light, but the conversion depends on the cosmological model. Astronomers use redshift because it is directly measurable from spectra and because it orders the universe into epochs. At redshift 0, we describe the present. At redshift 1, the universe was roughly half its current scale factor. At higher redshifts, galaxies are seen earlier and earlier in cosmic history. The exact look-back time depends on the cosmology, but the idea is clear. By measuring dark energy effects across redshift, astronomers are not only measuring distance, they are measuring how expansion changed as the universe aged. A universe with only matter would have a different relation between redshift and distance. A universe with curvature would differ again. A universe with dynamic dark energy would trace a slightly different curve from one with a constant lambda. The observations are therefore comparisons among possible histories. The sky shows one history, and cosmologists ask which equations reproduce it best. Error bars are part of that history. They are not decorations added to make a plot look scientific. They are the measured uncertainty from photometry, spectroscopy, calibration, intrinsic scatter, sample variance, and modeling. A claim that dark energy evolves must overcome those uncertainties. A claim that it is constant must also respect them. The honest graph includes the limits of what the data can say. Sample variance appears because astronomers observe a finite volume of the universe. If a survey happens to include more clusters, voids, or structures than average, some measurements can shift. Larger surveys reduce this by covering more sky and more volume, but the observable universe itself is finite from our point of view, so cosmic variance remains a fundamental limit for some measurements, especially on the largest scales. The existence of fundamental limits does not make the work hopeless. It defines the frontier. Some parameters can be measured extremely well. Others may remain limited by cosmic variance or astrophysical systematics. Dark energy sits in a demanding position because its physical nature may require detecting small deviations from a model that already fits well. The absence of an easy answer is not surprising. A careful narrator should therefore avoid saying that dark energy has been solved, and should also avoid saying that scientists know nothing. Both statements are wrong. The acceleration is well measured. The simplest model works well. The physical explanation is incomplete. New data may be hinting at change, but the case is not closed. These four statements can stand together, and the real story lives between them. That middle ground is more interesting than certainty. It is where instruments matter, where theory matters, where a supernova in a faint galaxy and a temperature ripple in ancient radiation can belong to the same question. It is where a small change in a parameter can alter the future of everything beyond the local group. Dark energy is not dramatic because it shouts. It is dramatic because its quiet effect is everywhere on the largest scale. When the final analysis of a survey is released, it may arrive not as a single number, but as a suite of papers, catalogs, likelihoods, covariance matrices, and public data products. Other teams will check them. Some will combine them with different datasets. Some will challenge assumptions. Some will look for overlooked biases. This is how a field protects itself from its own excitement. The public may see a headline saying that dark energy is changing, or that the universe may end differently than expected. The actual scientific statement is usually more measured. A dataset favors one model over another at a certain statistical level, under a specific combination of assumptions. That statement can still be important. It can still signal a possible shift. But its strength lies in the details that headlines often remove. For this reason, the most durable dark energy story is not one of instant revelation. It is a story of accumulating evidence and controlled uncertainty. It begins with faint supernovae, extends through maps of galaxies and ancient radiation, and continues into missions still gathering or preparing to gather data. The universe expands while the question remains open. And the openness is part of what keeps the measurements alive. A radio telescope contributes in its own way. Neutral hydrogen at 21 centimeters can trace gas across cosmic time when instruments are sensitive enough. Future intensity mapping experiments may measure large-scale structure without resolving every galaxy individually, using the collective glow of hydrogen as a tracer. This would add another map of expansion, another way to see the cosmic web not by starlight, but by faint radio emissions stretched by the universe. X-ray observatories add still another layer. Hot gas in galaxy clusters shines in X-rays, revealing the deep gravitational wells where matter has collected. Combined with microwave observations of the Sunyaev-Zeldovich effect, clusters can be detected and studied across great distances. Their numbers and masses are sensitive to how structure grows. Dark energy appears again indirectly through the population of the largest bound objects in the universe. The Sunyaev-Zeldovich effect occurs when cosmic microwave background photons pass through hot cluster gas and gain energy from high-speed electrons. The effect leaves a small spectral distortion in the microwave background in the direction of clusters. It is faint, but it can be measured. A cluster therefore becomes visible not only by the galaxies it contains or the X-rays its gas emits, but by the way it slightly changes ancient light passing through it. This layering of methods is one of the most important features of modern cosmology. The same cluster can be measured through galaxy motions, X-ray gas, weak lensing mass, and microwave distortion. The same expansion history can be approached through supernovae, bow, time delay lenses, and the microwave background. Dark energy is difficult precisely because no one method is allowed to carry the full burden alone. If the universe were smaller, younger, or simpler, perhaps the answer would be easier. But the actual universe is old enough for generations of stars to have lived and died, large enough for light to take billions of years to cross its visible structures, and complicated enough that every measurement carries astrophysics with it. Dark energy is measured through that complexity, not outside it. A distant galaxy in a catalog may have a redshift of 1.5. That number means its light was emitted when the universe was much younger and the scale factor was smaller. It may be forming stars rapidly, or it may already be aging. Its shape may be distorted by lensing. Its spectrum may be faint and noisy. In a dark energy analysis, it becomes part of a statistical pattern. But it remains a real galaxy, full of stars whose own local physics continues. A supernova at redshift 0.8 may be reduced to a point on a Hubble diagram, but it was also a thermonuclear event in a particular host galaxy. A bow measurement may be reduced to a distance ratio, but it comes from the positions of millions of galaxies and quasars. A lensing measurement may be reduced to a sheer correlation, but it comes from light bent by matter across the line of sight. The abstraction is necessary, but the physical anchors remain. That is why the subject can sustain a long journey. Dark energy is not one object to describe and leave behind. It is a thread through almost every large-scale observation of the universe. Follow the thread, and it leads from white dwarfs to galaxy surveys, from quantum vacuum questions to the far future, from a telescope mirror on Earth to the edge of the observable universe. The thread is invisible, but the knots it passes through are measurable. The next signal may not look like an answer. It may look like a slightly tighter error ellipse. It may look like a catalog with more galaxies than the previous one. It may look like a supernova sample with better calibration, or a weak lensing analysis with improved redshift estimates. Cosmology often advances by reducing the space in which wrong answers can survive. Dark energy may yield in the same slow way. For now, the simplest model says that the acceleration continues. The galaxies beyond our bound neighborhood recede into a future where their light becomes increasingly difficult to receive. The local group remains, stars continue their lives, and the wider universe becomes less accessible with time. This is not a catastrophe in the ordinary sense. It is the large-scale consequence of the expansion history we measure. The final image is still the observatory screen. A faint point brightens beside a galaxy, then fades. A spectrum appears, crossed by lines shifted toward red. A catalog gains one more entry. Somewhere else, a fiber catches the light of a galaxy, a space telescope measures a shape, and a microwave map holds the pattern of the early universe. None of it is enough alone. Together, it is how the universe tells us that its expansion is accelerating. The deepest name of dark energy is still unknown, but its effect has been written across the sky in distances, redshifts, maps, and horizons. The light keeps arriving from a universe that is carrying its unbound regions farther apart, and while the detectors are still able to receive it, the measurements continue. Quietly, carefully, one faint signal added to another, while the space between the galaxies grows.